Okay, record is on. So, few words about previous lectures. So, maybe once more time. All lectures or lecture records are in YouTube. So, they're here. So, this is the last one. So, today's lecture record will be here as well. Okay. What next? Today, I'd like to discuss about some very important issues about the power system and to use for this purpose FinGrid homepage. So Finland transmission operator or dispatcher homepage. Yes, FinGrid. From the first lecture, we saw the Latvian state transmission operator AST homepage, and for now we'll use FinGrid. What good information do they have? And the last one, what we'll see for today, I hope we'll have enough time for Italian blackout in year 2003. We'll discuss some issues about the Italian blackout, why it happened, and what to do to prevent these faults. Okay, first of all, in FinGrid homepage, let's look into the known parameters about the previous lecture about the inertia of the Nordic power system. So they have a special section for this purpose, because as mentioned, it is very important. Yes, inertia, it's our time about the speed of any process in power system, and as a result, a time of reaction. Yeah, how much time do we have to make any moves? So what do we see here? For example, inertia definition is the ability of power system to oppose changes in frequency due to resistance provided by the kinetic energy of rotating mass connecting to the system. The same as I told you, yes? During times of low inertia, large sudden power imbalance, for example, due to a sudden disconnection of a large production unit, causes large instantaneous frequency deviation, whereas during times of high inertia, the instantaneous frequency deviation is small. And there is a figure to show this, to border, how to say, values, yes, about this low and high inertia. The Nordic transmission system operator estimates the kinetic energy of the Nordic power system, Finland, Sweden, Norway, and Denmark. Yeah, but we need to highlight that, yes, they have their Nordic power system, but there is a Nord Pool, the trading platform, yes, where additionally Baltic countries such as Estonia, Latvia, and Lithuania are trading, yes, and we have DC interconnection, as it showed here, yes, with Finland and Sweden. That means that we are integrated in this Nordic power system. For us, for Latvia, of course, you understand, we are in Latvia, R2 is Latvian State University. I'll use Latvian example all the time and what is going on around, yeah. For this understanding what is a power system, this balancing problem, this inertia, and so on. So, yeah. Okay, yes. The data represents the total kinetic energy of the Nordic power system, as the behavior of frequency is primarily influenced by the total kinetic energy of the system. Again, yes. as to say, let's repeat once more time, yes, but this is very useful, yes. So we calculate, and I showed you last time, yes, how we calculate, yes, taking in account all this rotating mass, yes, all these rotating power generators, yeah, to calculate the kinetic energy of the whole system. The kinetic energy of the Nord power system typically varies between 120 gigawatt second and 280 gigawatt second. Here you can see one more unit type, how to represent this inertia. So this is power seconds. Yes, this is. In the low inertia situation, the Nordic TSO, transmission system operator, yes, this means procure fast frequency reserve to prevent this instantaneous frequency deviation become too large. And this is why we started to talk about the inertia. Yes, so inertia is our time. How much time do we have to make a move? But what types of moves could we do, yeah, in a normal operation situation? Last lecture we finished with this under frequency automation. This automation means that in normal operation mode we can't do nothing, yes. So we used all our tools, yes, to deal with this problem. It looks like a fault situation and we need under frequency automation, yes, to deal this on normal mode. But in normal operation mode, we have standard tools, yes, to deal with this. For example, they have very good features. For example, we could see here this inertia in time, yes, how it how this inertia, yes, deviates, yes, during the time. Here is very interesting feature as well. For sure, you could go to this site, yes, to visit this site by yourself and to study, because it is very interesting, very useful, yes, about this critical situation that was on 13th of June in 2021. Yes, the situation, here it is, the Nordic inertia dropped to 100 value 110, or opposite situation, for example, that it is 258 gigawatt seconds, yes, very interesting, yes, to study. But we are going next, and we're interested in this, in frequency regulation. About what are these tools, yes, for frequency control in normal operation. Here is a small video.
Reservimarkkinatoimijat voivat ansaita tarjoamalla.
Yeah, but it was in subtitle. It is Finland, yes, but oh, there was a subtitles in English. Oh, doesn't work for now. Okay, so we didn't watch. Okay. No subtitles for now. Okay. Some, I think, YouTube issues. There was, how to say, automatic generated subtitles into English, so it was possible to turn. Sorry. I think it's okay. Only Anup, only you can't hear me, or everyone can't hear me? Hello, students. Do you hear me? Okay, now it's okay. Maybe some troubles with wireless internet and the faculty. Okay. It's okay now, so fine, let's move on. Okay, and the first one is a frequency containment reserve. So it calls FCR. Every type of control has its own name, its own abbreviation, yes, short name, very useful to know, to show that you are a specialist, yes, you're a master. Let's look inside what does it mean. So frequency containment reserve for normal operation. I need to highlight normal operation, yes, or FCR N, so normal operation, and frequency containment reserve for disturbances, or FCRD, are active power. But these disturbances, yes, is still, yes, in the border of normal operation. So there is no, how to say, fault condition, yes. We still don't know. Okay, we have a disturbance. Disturbance is not high to run this out of step automation, yes, and so it means that we are still trying, yes, to use these tools, yes, to recover the frequency. Are active power reserves that are automatically controlled based on the frequency deviation. Their purpose is to contain the frequency during normal operation and disturbances. FCRN aims to keep the frequency within the standard frequency range of 49.9 to 50.1 Hz. So you see the range of deviation very small. Yes, the normal is 50, so the deviation is 0.1. Yeah, very small. And if CRD, so in this range we can consider there is no deviation. Yes, it is normal operation, no deviation. And if CRD aims to limit the frequency deviation from 49.5 to 50.5 Hz when the frequency goes outside the standard range. Yes, see, the outside of standard range. This is standard range, this is outside the standard range. FCRN is a symmetric product that must be capable of both up and down regulation. Up regulation means increasing power production or decreasing consumption. Down regulation means decreasing power production or increasing consumption. The FCRD divided in separate up and down regulation product. So technical requirement, yes. Minimum bit size. So this is very important. This is how to say the regulation step. It means that how much power is in our tool to do this. So oh, sorry, not at all how much power, but this is a regulation step. This is very important because, as you understand, we need any regulation for recovering. Yes, if we use the step, okay, the power that is not enough, the frequency is still not equal. And if we use too much power for regulation, it means that we have over-regulation, yes, and it means we don't have the nominal frequency as well as a result. So that's why this step is very important, yes, to make this accurate, precise regulation. Yeah, and what is written here? Activation performance. Tested with the sine wave test in frequency domain. Yes, you understand the issue. In domain approximately 63% per minute and 95% per minute with the step, yeah, of 0.1 hertz frequency change. Yes, we see this frequency change. This is our regulation minimal step, and this is the activation, yes, the demand, power demand activation. Yes, okay. Frequency containment reserve for disturbances. This is D type, yes. Minimum step is 1 megawatt. This is, you see the difference, yes, because normal regime, it's okay, we have time. This is disturbances. We have disturbances, we have much lower time for a move, for a decision, yes. but okay, this is automation. Decision making is more for, how to say, for human being. This is automation. That means that there is an algorithm. We see, how to say, what is going on. We see a set point. We make a move. Yeah. So for this type of automation, let's say, is to make a move more correct. Okay, this is times, and this up and down are the same. The result, how the parameters are the same, just they are separated about up and down as we have written. Okay, I think in short, it's enough. Let's go next. Fast frequency reserve, the next type, FFR. The fast frequency reserve is procured to handle low inertia situation. Inertia means the ability, no, the same, once more time, of the kinetic energy stored in the rotating mass in the electricity system to resist change in frequency. The operation of the power system follows a dimension principle according to which the loss of a single electricity production unit of high voltage DC link must not cause the frequency to fall below 49 Hz. And this is very important, this value, yes. The magnitude of the transient frequency change following a disturbance depends on the magnitude of the power change caused by the disturbance, the system inertia, and the speed at which the reserve are activated. The needed follow of the fast frequency reserve depends on the prevailing inertia in the power system and the size of reference incident. The fast frequency reserve has been implemented in Nordic in May 2020. Fingrid pursues the reserve for a national market in order to participate in the market. So this is one very important thing. Yes, the frequency regulation is a part of the market. So it means that we are not only trading the electricity at the market, but we are trading the service of keeping the system operation at the market. So this is a tool how to keep the system in operation. This tool means the ability to use power. So that this power for this FFR, fast frequency reserve, is trading at the market as well. No, and to recap all of this into words one more time. So yes, we need fast regulation when we have low inertia situation. Low inertia means that we don't have enough time for a move. Yeah, that's why fast frequency regulation. So here let's look the technical requirements. Yeah, for this regulation, the reserve units participating in the maintenance of the fast frequency reserve must meet the technical requirements for the service. No, this is clear because it's market. It means that everyone, yes, who admit the criteria, the requirements, could participate and sell this service. Yes, that's why for all this we need the requirements. Yes. Compliance to the requirements must be demonstrated by the pre-qualification test before market participation. The activation of the fast frequency reserve is based on the automatic local control. Fingrid does not send control signals. The reserve unit must have a control that adjusts the power based on frequency measurements when the unit participates in the maintenance of reserve. And for this, there is a very interesting example for this service. Some years ago in Finland, Siemens built a hypermall, yeah, shopping mall. For their purpose, there is battery storage, yes, for how to say, for all these automation systems that are in a mall, for this ventilation, air conditioning, heating, lighting, and so on. So automation and so on. So they have a really big battery storage. And this how to say mole is this is how to say a pilot project, yes, designed by Siemens, is participating in this fast frequency reserve. So this mole, yes, because they have battery storage, it means that they have stored energy. They have these lithium batteries. That means they have a fast reaction speed. You understand, you know, that the lithium batteries, yes, can operate very fast and to push the energy to the grid or from the grid, yes, if it is important, because we can charge or discharge approximately, okay, in the fast mode in an hour, yes, approximately in an hour we could fully charge and fully discharge this, how to say, storage, battery storage. And this mode with this storage capacity participates in this frequency regulation. Yes, they sell their service, their ability, yes, to push energy to the system or to get energy from the system in a case, yes, when it's important. So there is so very interesting this pilot project made by Siemens in Finland. Okay, so this is activation frequencies, yes, max activation time, yes, you see the criteria. So you need to follow the frequency and you have the limit of time, yes, how fast you should react. The minimum duration of activation is 5 seconds. In the power deactivation rate is no more than 20% of the FFR capacity per second. In the deactivation rate is higher and the minimum duration of activation is 40 seconds. The reserve unit must be able to reactivate within 50 minutes of the previous actions. The technical requirements and the verification of the regulation capability of the reserve unit are described in more details in the document. Yes, you could see, if you're interested, yes, to look in details, yes, this documentation about these procurements. Okay, let's go next. The next is automatic frequency restoration reserve. Yeah, AFFR. In the year 2040, the Nordic TSO, one more time, is transmission system operator that keeps the system in operation. Yes, this is its task. Introduces a new type of reserve, automatic frequency restoration reserve in the Nordic power system. Its purpose is to return the frequency to the nominal value of 50 Hz. FRR is a centralized, automatically activated reserve. Okay, this is very important. What is the difference? Yes, this is automatically activated reserve. It centralized, sorry, this means centralized automatically reserve. It activates based on the activation request signal sent by the TSO. The activation request is calculated based on the frequency deviation in the Nordic synchronous area. No, should to add not only the frequency deviation, but the deviation speed as well. The minimum capacity of regulation is 1 megawatt and full activation time is 5 minutes maximum. And there are as well technical requirements that you could read by yourself, yes, to improve your knowledge. Fingrid purchases AFRR reserve from Nordic Capacity Market. AFRR is produced for hours during which the frequency tends to vary the most. The procurement hours are informed in advance. When? The question is when, the main question for this, yes. A balance service provider can submit bids to the capacity and energy markets separately for up regulation and down regulation. Capacity payments is determined based on the price of the most expensive accepted bid, and it is paid to the balance several provider. Energy fee based on the energy market activations, and it is paid to the balance service provider according to the marginal price of the market period. Regulation energy is correct for the balance responsibility part of the reserve resource. Okay, and in this case, maybe should be useful to come back to the energy market and the idea how to determine, okay, how the price, the node hourly price is determined at the market. Because as you just saw, there is the similar rule how it is made. So, for example, from the economic, and because the market it's economic, yeah, you know that if we want to find the balance price, yes, we need to see where this offer and demand curves, yes, goes together. This is how to say the balance price. And for electricity, the situation is the same with one different. For example, you have a demand of 100 megawatts. And you see, you have, for example, three types of generator. Hydro, for example, CHPP, and, for example, gas CHPP and coal CHPP. Hydro power plant could sell you electricity at this hour with an offer of 50 megawatts with the price, for example, 10 euros per megawatt. Natural gas CHPP could sell, for example, 40 more megawatts with the price 20. Okay, it's too less. Okay, for example, it will be 40 euros for megawatt. So 50 from hydro, 40 from CHPP gas, natural gas. But the total demand is 100. And the third one, coal could sell, for example, 100. Okay, too much. 50 more megawatts with the price 100, for example. So we have price 10, 40, 100. And it means, for example, if okay, we could buy from HPP, but it's not enough. We could buy from CHPP more. In total, it is 90, not enough. We need to buy 10 more. Yeah. So it means that we will buy from these three power plants, total amount of 100 with a price 100, because the total price will be defined by the power plant with the higher price to cover the demand. Because how to say, it's like how it is in this stock market, this is how to say the golden bill in stock market. Yes, so without this 10 from coil CHPP, we could, yes, satisfy the demand. That's why in the market, yes, the total price will be 100 euros, yes, for this 100 megawatts. That is the demand at the hour N. So that's why there is a very easy law. Yes, so the power plant with a higher price will determine the price if we need it to cover the demand. Yes. And in this way, the action for any type of services, yes, in the market is similar in this way. Okay, but let's come back to this, how to say, frequency regulation and the reserve. As we understand, yes, the reserve is a power. To restore the frequency, we need a power, and this power we sell, yes, with the same principle, but at the separate, no, not separate, but the specific at the specific market platform for this purpose, yes. And then just I want to show you what are the prices electricity market for this for balancing state area operation disturbances information balance description of balance model imbalance fees. Or for example, see balance service fees, fixed weekly fee, volume fee for production and consumption, and imbalance fee. This is fees. And what else I need to, I want to show you these features with this balancing prices. Operation disturbances. I need to find them because I know they are here. European cooperation, reserve power plants, reserve trading. Okay, this is who is participating. We'll go there, but I just want to show you the feature balance injury beats. How it works, pricing. Okay, yes, we'll maybe grid. Power maintenance systems transmission. No, price should be here in market. And this is about the model. Okay. Maybe I'll find something. Oh, yes, where it was. Fast frequency reserves somewhere here. Okay, volume and price. Okay, the search helped. Yeah. Okay, maybe we need to open one more. For example, let it be AST. What? Let's look using this home page from Latvian operator. Let's switch to English and market. Electricity transmission power system. Okay, let's look inside. Let's look inside. What is going on? Yeah. What is going on? You see? We see the situation, as I mentioned, for example, for Norway, yes, they have their own, okay, they are profit city, yes, they produce electricity by themselves, they have a lot of rivers, mountain rivers, so hydropower that produce more they than consume. That's why they have low prices. The same situation is for Sweden because they have nuclear power, they have wind, they have hydro and so on, great potential, and their business is to sell electricity. Yes, that's why for their use, yes, they have such a lower price. And opposite situation for Finland, Estonia, Latvia, and Lithuania, because these countries don't produce enough electricity, yes, they need to buy. And the possibility to buy electricity is based on the transmission capacity limits. Yes, so if you have any type of limits, that means that price goes up. For example, for Finland, you see it is quite high. If we compared to Sweden because they buy from the region with a price of 19, but they buy for price 203 euros for megawatt. And the same situation is to Estonia, yes, because as Estonia, you see, because Estonia sells electricity to Finland, yes, that's why they have this price, because they want to sell electricity to Finland with a price 203, and they sell electricity, yes, that comes from Lithuania, Latvia, you see the flow, Poland, Lithuania, Latvia, Estonia to Finland, yes, so this flow comes from Poland, the same, almost the same value comes to Latvia and goes next to Estonia, yes, so they're selling electricity to Finland, yes, because have capacity limits, yes, to get this electricity from Sweden, yes. So that's why the situation when you don't produce enough by yourself. And let's go here and let's see. Okay, I need to reset. You see, the price is 200, but we see that the fluctuation, yes, for the balancing power, yes, is quite different, yes. It is not the same. It could be very high or low. Basically, in condition that you have not enough power, you have any disturbances, stochastic disturbances, yes, unpredicted, it is much higher. Because here we need to start to talk about, okay, you have a plan, how much you will consume, you have a bids, yes, to the market, to the pool, you have offers, you have agreements to buy that amount of electricity in every hour, yes, but you have a real life when the consumption is not the same as predicted, and you have this balancing power to deal with, how to say, this is a difference, yes, between your plan and the reality. But there are some issues that can make troubles. First of all, you were planned, or your partner, your partner, yes, from who you buy electricity for the hour N, yes, can't produce enough power as it is in agreement. Or you, because, for example, for your country, yes, for your state, your internal production, it's, how to say, they are independent players at the market. For example, if your energy company is a state company or belongs to states, whatever, this doesn't mean, because they are participant of the market and they play using market rules and laws. So that's why I can talk any participant, yes, who is buying or who is selling electricity for hour N, yes, to the, for example, as it is here, system, Finland power system, yes, and they can't produce enough as it is an agreement. They have any troubles or something else. What to do in this situation? Yeah, of course, there is a solution for such problems. There is a special market for such things. It calls that there are two types of markets: intraday market and day ahead market. So in this intraday market, they could buy electricity from other participants. For example, I sold 100, but my capacity is 200. No, I'm a player, yes, I have any type of power plant. I'm a player, yes, I sold only 100, but I have possibility to produce more, but there were no demand, yes, to buy more. That's why I sold only 100 or with my price. So I have 100 more. And in this case, that any player can't, how to say, produce enough, they could buy from me because I have possibility to produce more. Yes, to make how to say to balance their problems. In this way, the question is, what is the price for my service that I produce more to cover, yes, another player problems? And for this market, there is special pricing, yeah, special platform and special pricing for this platform. And for transmission capacities play significant role in this pricing platform as well, because okay, I can, as you saw from this, I can produce more. I would like to sell to you, but how to deliver? Is it possible to deliver this electricity? Yes. What about these transmission capacities? So that's this equation. So maybe to recap one more time. So this is in the situation, this is standard normal balancing, yes. So we are not now talking about this frequency, yes, frequency operation, frequency control. We are just talking about how this system works. This is a small, how to say, off top, yes. But just to be more clear how all this together works, I decided, yes, to discuss this. So to recap this market pricing issues, yes, in normal regime, we have when our prediction of consumption is not the same as we planned, we have this balancing, yes, to cover this imbalance. But in issues, for example, when any player can't deliver as much electricity as it is in agreement, yes, we have a separate market, yes, to buy where it is possible, yes, to cover these problems to this player who can't deliver enough electricity. And we have separate market for this regulation, yes, who participates in regulation, and all of this frequency regulation on here. And for this regulation, yes, this regulation balancing prices, yes, are here. And here is a very interesting, yes, curve about this deviation, about this fluctuation of this price, how much this price could be. Here you could see this is a price, yes, for 1 megawatt, yes, 450, yes, very, very high. Okay, so yes, let's go back and let's look inside this balancing energy and balancing capacity markets, MFRR. Fingrid maintenance, sorry, Fingrid maintains a balancing energy market together with the Nordic transmission system operators. A reserve provider is obliged to give an amount of regulation bids which corresponds to accepted capacity bids to the balancing energy market in exchange for a financial compensation. A balancing energy market contract with Fingrid is needed to participate in the market. The Nordic TSOs activate bids on the balancing energy market whenever necessary during normal operation or disturbances. Activation is done manually from Fingrid's main grid control center. And here you see this manually. In previous time, there was this classification about primary, secondary, and thirdly type of frequency regulation. Yeah. So the main two types, yes, was primary and secondary. Primary was for a normal operation mode. Secondary was for it is a fast regulation for normal and fault operation, like auto frequency, yes, automation. And the third is manual, is slow manual operation. But for now, maybe in the literature you could see this definition about this primary, secondary, and so on. But time goes on, and for now, for Europe, yes, these new abbreviation, new names are actual, yes. So the balancing capacity market was introduced in the spring of 2016. A reserve provider whose capacity bid is accepted on the balancing capacity market is obliged to give up regulation energy bids to the balancing energy market in the exchange of the financial compensation. The balancing capacity market is used to secure that Fingrid was sufficient amount of manual frequency restoration recovered to cover the dimensioning fault also during maintenance of Fingrid oven and listing reserve power plants. Okay, and this is how it works. Balancing energy bids may be given for all resources that can carry out a 5 megawatt change, this is amount, of power in 50 minutes, 1 megawatt if using electronic activation. The bids are given to Fingrid to later than 55 minutes before operation hour in no, it means, you see, this is hour n, and it means 45 minutes before, according with the balancing energy being instructions. Balancing energy bid should include the following information about adjustable capacity: activation hour of the bid, power price, and name of the balance resource, name, regulation, object identification, as well as transmission area in which the resource is located with the determined the information exchange platform for each balancing resource. Balancing energy bids are either up-regulating or down-regulating bids. In case of unregulating, the resource owner either increases production or decreases consumption and therefore sells energy to Fingrid. You see, there is one more, no, you see, this is very important. So possibility to decrease consumption is a service as well, yeah? Because it is the same for power system. You need to keep it in balance. So you need more production, yeah, or less consumption. So to decrease the consumption is a service as well. In the case of them regulations, the resource owner decreases production or increases consumption and buys energy from Fingrid. The Nordic balancing energy bid list is prepared from a balancing energy bids by setting the bids in order of price. The balance management and frequency maintenance, the balancing energy bids are used in order to price to the extent allowable by the operation situation in power system. Of the upregulating bids, the cheapest is used first, and correspondingly the same as I described it with this power plants and the piping systems. Yes, the cheapest is used first. Correspondingly, for down regulation bid, the most expensive is used first. Yeah, because the operation situation and bid cannot be used in the if is then left unused. No, that's pricing is less interesting. Reserve trading and information exchange. The precondition for participating in Fingrid reserve marketplace is the right and correct exchange of information between balancing service provider and Fingrid. Information exchange requirements and implementation vary slightly between different reserve markets. You see different markets, yes? So the main information exchange platform between balancing service providers with Fingrid in the VAX system. VAX is, no, this is their special system. Is an internet-based application where reserve suppliers, after receiving a user ID, can, amongst other, submit reserve bids to various marketplaces. Accepted bids are also stored in this vaccine. No, this is about more the platform. And reserve power plants. Reserve power plants, you see. Not all the power plants are participating in this regulation, as I said before, and only special. Okay, you see the map where they are located and this available powers. But okay, I think it is not very interesting to look this in details because obviously this is about the Finland, about the situation at this, how to say, at the moment. This could change, but the idea, so yes, power plants, what for reserve. Okay, what else? What else for Fingrid? What else is interesting? What else is interesting? Okay. Okay, yes, I think this enough, and let's look inside the blackout as I so I was planned to discuss this big blackout in Italy. Okay. Okay, for Italy, I will use information for me in Latvia because I want to describe this blackout in details, but shortly, yes. For you, you could Google this Italian blackout. Because there is a lot of reports. This blackout is discovered in details. You could find but information in Wikipedia, yeah. So there is a lot of information in details. As I remember, the standard report for this blackout is about 48 pages, yes. So for sure, if you're interested, you could read it. Very interesting information. But for us, we don't have enough time for today. I will try to describe very shortly, but in details about this Italy and what was. Okay, I want to find the map of Italy. Italy, there is a map. I remember there was a map. Okay. Maybe for you, I need to open the Google Maps. Google Maps, and just to show you the Italy and how it looks like. Because this is very important in understanding. So you see, this is Italy. This is Italy, yeah. And based on the geography, yes, Italy is connected to the Central Europe only in the north. And this connection is limited. So it is connected to the France, Switzerland, Austria, and Slovenia. So yes, this is limited connection and only in the north. And as a result, the interconnection is only in the north, and possibility to get more power through another countries comes from the north. This is the main idea. So this is part of Italy and this connection. So these lines, you see, this is read with this red color. Yes, this is from France. We have three lines. Switzerland, okay. Red color, this is interconnection. We have a list from here. Okay, so three transmission lines from France with the voltage 380 kV. So you understand, the higher voltage, the more power we can to transfer, yes, to transmit. Switzerland, two lines, color, two lines, Switzerland, the red color. Okay, you see this is red color, two lines, and 220 kVs, green lines, yes. The total number of connection is 220 kVs, France 1, Switzerland 6, Austria 1, Slovenia 1, and one DC cable, but its capacity not big, only 500 megawatts to the Greece. The main idea that for that situation, Italy is a deficit country, basically. So yes, it produces not enough electricity. Yes, I want to find the table. So the total demand for Italy was 27.4 gigawatts, and the total self-generation, okay, where it is, total self-generation for Italy, I want to find the correct value, where it is. Okay, whatever, it's about 20. Because here you see the import, yes, 7. Okay, there is a total, yes. So they need 27, but 7 they are importing from the north, from the countries from the north, yes. So they produce by themselves about 20, and this about 7 gigawatt of energy they are buying from the north. And what was the situation? At the night, at 3 p.m., yes, 380 kilowatt transmission line from Switzerland, yes, due to the overload, the temperature of this wire was too high, yeah, due to the overload, and as a result, the wire length, yes, as we know from basic physics, yes, the higher temperature, yes, metal becomes longer, yes, becomes longer, and as a result, due to this length increase, the wire touched a tree. As a result, it's a fault, it's a ground fault, and relay protection disconnect and overload lines. What to do? No, basically, we need to import 7 megawatts. We need minus one line. It means that this power is separated to all other connected lines, yes, because we need to deliver 7 gigawatts. It means all other lines started to deliver more, because we will have lost this 380 kV line. As you know from the relay protection, there is a recloser. Yes, it is possibility to reclose. The automation tried to reclose this line back, but without a success. Because there is these lines are interconnection with different countries, and due to this disconnection, the angle of EDS vectors from Switzerland and Italy become too big, this angle between two vectors. As a result, there was no possibility to reclose this line back. So this reclose is not happened. Manually, this was important. Manually as well, it was impossible to do this. Let's see the timing. This is 3 o'clock p.m. Sorry, a.m. It's after midnight. It is in the night. 24 minutes later, we lost one line. It means that all other lines had more overload, and as a result, one more time, due to the overload, 380 from Switzerland disconnected as well, because it was overloaded by 10%. The total load is 110%. So we lost one more line. No, and the result, all other lines are more overloaded, and step by step, one by one, all of these lines that connect Italy to the north, to the countries, to the Central European countries, all of them are disconnected. What we got? Italy is by itself, with only its own generation of 20.7 megawatts and the consumption of 27 megawatts. What to do? We have a really false situation. Italy is disconnected from the Central European system with no possibility, how to say, to get energy from anywhere else. So this is the task for this under-frequency automation. Under-frequency automation. For Italy system, they have enough power connected to this under-frequency automation to deal with such a problem. And let's look how it was. So, to the first step, no, we could call it stage of this under-frequency automation, is connected about 50 to 60%. Okay, sorry, this is total to this automation is connected to 50 to 60% of the load. So if the total load or demand is 27, for example, it means that about 12, 13, maybe 15 gigawatt of load is connected. Okay, so with the frequency drop to the value of 14.9.7, activates the first stage of this under-frequency automation, and in the range of 49.7 to the 49.1, the total demand, no, total power of 6 gigawatts will be disconnected. These are pumps for the hydro pump power plant, HP hydro pump. It means that they can pump the electricity up, yes, to store this water and to use it when it is needed. So the deficit about 7, only by doing this they could disconnect 6. And let's come here to look this diagram, because this diagram shows in more details what is going on. So okay, where I need, okay, maybe so here we see the frequency. This purple is imbalance, this blue is frequency. So what's going on? Here we could see the imbalance. Yes, this is the values of power. Yes, you see Italy is disconnected and the total imbalance is this 7 gigawatts. Here we see this. Time for under-frequency automation operation. Yes, to this time we see how the frequency dropped. Under-frequency automation activated and started to disconnect the load. If we disconnect the load, it means that imbalance is decreasing. And here we could see for the time, okay, this is 3 hours 25 minutes. This begins 25 minutes 40 seconds, and at the time 3 hours 26 minutes. So it means that in 30 seconds, under frequency automation is disconnected enough load to balance the system. So we see at time 3 hour 26 minutes, the system is in balance. Production is equal to the consumption. But what is going on with frequency at the same time? We see that the system restores the balance when the frequency with the value 40 lower. It's lower than 48.5 hertz, about 48.3 hertz. And as you remember for previous lecture, as I showed you the figures, when we have time limitation, then it is possible for the generator to operate the time limit for generator operation with the lower frequency. So we remember we have time limits, yes, for almost all kinds of load and generation to operate with the lower frequency. And as a result, yes, here we have a table with generator disconnection by the protection, by the relay protection, because every generator is very valuable and very expensive unit. It has its own protection as I mentioned before, and the protection will disconnect the generator from the grid if we have any problems in the grid to save the generator. And here we see these are the number of generator and the total power that was disconnected due to the low frequency. Here are some issues why it was. There are a lot of different issues why it was disconnected due to the low frequency in the system. This cooling pumps for this generator, for the CHPPs had not enough power because lower frequency, lower power from these cooling pumps, voltage drop, and so on. So different issues, but the main idea, due to the lower frequency, generators was disconnected by its own protection. Here is a list of number and total power. Disconnect, 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 disconnect. So the problem, we have a system in balance. Yes, very good at this time moment. Yes, but frequency is low, and it is low for 30 seconds. From this time period to this time period. Yes, 40 seconds. It is low for 40 seconds. And generators started to disconnect due to the low frequency. And what we could see here, that under frequency automation have have more stages, yes, to disconnect more load. And we see that frequency, yeah, continue to drop due to, you see these fluctuations here. So generator disconnected, we are in balance, frequency drop. As a result, new stage, new disconnection from the under frequency automation. And all this fluctuation, this time is 26 minutes, and you could see this 28 minutes. It means during 2 minutes, under frequency automation used all this possible stage, disconnected all the possible loads, but due to we lost every second more generation, result frequency dropped to a critical value, then the disconnected everything and it was blackout, no electricity in Italy at all. Power system was stopped to exist as a united system. So it was blackout. What is the main, how to say, conclusion from this? At this point, when the under frequency successfully restores the balance in system, to restore the frequency was as operator a human being task. So at this moment, under frequency successfully restored the balance, but with a low frequency. Now it was the task for a system operator to make moves to restore the frequency. But you see how much time it was to a human, yeah? Very low time. Plus, it was night, it was stress for human, and so on. Of course, all operators have instructions what to do in this, in case of this situation, and so on. But we see the result. If they had the under frequency automation second part, this is 2, yes, which is responsible to restore frequency automatically without involving an operator, yes, this blackout could not happen, because in this point, under frequency automation will continue to automatically disconnect the load to keep the generation more than the consumption and to restore the frequency. And the frequency could be restored at this time in about 20 seconds more. And Italy will keep its operation in an idle mode, yes, by itself, with enough generation. With all this generation in operation, and the human operator task was, could be to try to reconnect Italy to the Central European countries. But they have no automation, this under frequency automation to restore the frequency. They have only to restore the balance. And as a result, the blackout. That's why, from my point of view, this second option for under frequency automation with frequency restoration in automatic mode must be. But this is, how to say, the philosophy, how to design your, how to say, power system protection. Okay, so this is in details, but very shortly, because we don't go inside about all the issues why every generator was disconnected. Yeah, and then the issues why the human operator, yeah, couldn't find for this critical, you see, 2 minutes, yes, the this period of 2 minutes, yes, all happened by 2 minutes, yes. So it means that for human operator, there was only 2 minutes to deal with this problem. So in 2 minutes, it was a blackout. So by 2 minutes, human operator could not, because it was in past, could not, yes, make right moves, yes, to save the system. Okay, that's why the philosophy, when in case of emergency, it is better to have an automation to help human to deal with this. Okay, I think it's time for today because we worked without a time break. Maybe you have any questions? I can stop the record. Okay, stop the record, stop the record.